Hello, everybody, and welcome to Technology Today at ohmTown.com. I am Mayor Watt. I run ohmTown.com, and normally I would be hosting this with the sentient AI from the future, but they are not available today. So it's just me talking about these 5 articles: a new pain relief discovery, carbon capture efficiency, energy density breakthrough, fractionating crude oil, and Earth's hydrogen jackpot. That and maybe some snark on the other side of this. Hello again. In case you missed it, I'm Mayor Watt. I run ohmTown.com. And this is the front page of ohmTown.com for the 24th. We're actually in the 25th, so we can drop this down to the 25th and hit OK in our show. And you get snapped into another time. So all of the articles are going to be from the 25th. That said, you can go over to Technology Today over at ohmTown.com. So it's a subgroup. It's one of the many. There are 50 that are under 6 main categories. You get a 7th icon if you become a citizen. There's more stuff in there. But in here, you get things that have been deemed appropriate for Technology Today, although we sample from across the entire site. They get put in different places for different reasons. But anyway, the first article that we're going to talk about today is what I call a pain relief discovery. And that's because Tylenol doesn't work the way that we thought. Scientists just made a surprising pain relief discovery. Scientists have just upended decades of assumptions about how Tylenol works. A new study reveals that the common painkiller doesn't relieve pain by increasing natural feel-good chemicals, as once believed, but by lowering one of them. This surprising reversal could open the door to a new generation of safer, more effective pain medications and reshape how we manage pain. The article is over at Indiana University. The article is hosted at scitechdaily.com. So the new discovery, it says, from Indiana University, is a study led by Michaela Devarakova and Alex Stryker at UI's Gill Institute for Neuroscience. It was published in Cell Reports Medicine, and the new findings reveal a previously unknown way that acetaminophen, the active ingredient in Tylenol, targets pain in the body. The team discovered that acetaminophen blocks an enzyme responsible for producing 2-arachidonyl glycerol, or 2AG, which makes it a whole lot easier to pronounce. This compound is part of a group of naturally occurring pain chemicals called endocannabinoids, which activate receptors in the body known to influence pain, mood, and even the effects of cannabis. Although Tylenol is most commonly used medication for pain and fever in the United States, its exact mechanism has remained uncertain for decades. There are hypotheses, but we still don't know precisely how it works. Up until now, they thought that it elevated endocannabinoids in our body meant less pain. But their study shows that in the case of 2AG, it might be the opposite. Actually, reduced levels of 2AG lead to decreased pain. So if you don't know what the target is, you can't design an alternative. Their research suggests that the enzyme might be the target, in which case you could start developing drugs that target that specific enzyme, but without that toxicity, because it can cause liver damage. And too much of it can be acute. So going forward, the research team is looking to evaluate other common pain relievers like ibuprofen and aspirin to determine whether they have similar mechanisms of action. All right. The next article is over in Technology Today as well. It's from SciTech Daily as well. MIT breakthrough makes carbon capture 6 times more efficient. MIT researchers have developed a powerful improvement to carbon capture tech by using nanofiltration membranes to separate key chemical ions, drastically enhancing efficiency and stability. This clever middle step allows both capture and release phases to run more effectively, potentially cutting costs by 20%, making the process more forgiving to fluctuations as well. So the article again is over at SciTech Daily. David L. Chandler, Massachusetts Institute of Technology, put this article together, and it says the clever middle step allows both capture and release phases to run more effectively, potentially reducing the cost by 20%. So now researchers at MIT have discovered a clever way to overcome this challenge. They say it's a balancing act, and improving one part usually means weakening the other. But by adding a nanoscale filtering step in the middle of the carbon capture process, they've managed to boost efficiency by a factor of 6, while also lowering cost by 20%. That's the key ingredient, which I think is kind of lost. It's not just 6 times more efficient, but it's doing so at a 20% reduction in cost as well. So on the flip side, compounds that let go of CO2 aren't great at capturing it. So you can catch some, but not necessarily release it. So it's a balancing act, and improving one meant weakening the other. So it says traditional systems often use a chemical called hydroxide, which quickly reacts with carbon dioxide in the air to form carbonate. The carbonate is then sent into an electrochemical cell where it reacts with acid, turning into water and releasing pure CO2. The result is a clean, concentrated stream of carbon dioxide that can be reused for making fuel for other valuable products. However, there's a major hitch. Both the capture and release stages happen in the same water-based liquid, so the capture step works by a liquid full of hydroxide ions, while the release step needs the liquid to contain mostly carbonate ions. So as you can see, the two steps are at odds. These two systems are circulating the same sorbent back and forth. They're operating on the exact same liquid, but they need two different types of liquids to operate optimally. So it's a small 3-part system. And it says if you don't separate these hydroxides and carbonates, Rufer says, the way that the system fails is that you'll add protons to hydroxide instead of carbonate, so you'll just be making water rather than extracting carbon dioxide. That's where the efficiency is lost. So they're basically scrubbing the carbon out easier. They say that Varanasi adds that the really nice thing about this is that we've been able to do this with what's commercially available and with a system that can easily be retrofitted to existing carbon capture installations, and costs can be driven down to $200 a ton. It could be viable for widespread adoption. Rufer notes that people are buying carbon credits at a cost of over $500 per ton. Let's keep going. The next article is over in Technology Today. Metal fleeces boost battery energy density by enabling thicker, faster charging electrodes. So batteries are becoming more and more powerful. A discovery by researchers at the Max Planck Institute for Medical Research in Heidelberg could now give them a significant energy boost. Call them metal fleeces. Stephanie Baum wrote, and it was reviewed by Robert Egan. A team led by Max Planck director Joachim Spatz has discovered that metal fleeces used as contact material in battery electrodes significantly accelerate the charge transport of metal ions in particular. This means it's possible to build significantly thicker electrodes than a standard one today. It means that roughly half of the metal contact and other material that do not contribute to energy storage can be saved, and makes it possible for researchers to significantly increase the energy density in batteries. And the findings are over at ACS Nano. The active material is the actual storage material that absorbs and releases the charge during charging and discharging. Today, battery manufacturers use graphite in the negative terminal and various inorganic compounds containing lithium in the positive terminal. The active material is porous so that it is penetrated in the liquid electrolyte. So they say it's a new approach, accelerated ion transport through an electrical double layer. So in the study, Heidelberg's team has now shown that electrodes can be produced at least 10 times thicker than it is usual today. and still charged and discharged quickly. The researchers have demonstrated the lithium ion strips of the molecular shell on a copper surface deposit themselves there and form an electrical double layer with electrons that accumulate under the metal surface, known as the Helmholtz layer. All right. They say they have a chance to catch up with Asian manufacturers and be even better, according to this article. Let's keep going. The next article is over in Technology Today as well. A new approach could fractionate crude oil using much less energy. So if you don't know how gasoline and various component petroleum products are created, it's distilled just like alcohol is, except that it's oil and it's broken off into its component parts, just like heads, hearts, and tails. Separating crude oil into products such as gasoline, diesel, heating oil is an energy-intensive process that accounts for about 6% of the world's CO2 emissions. Most of that energy goes into heat needed to separate the components by their boiling point. Stephanie Baum, once again, put the article together for techexplore.com. Robert Egan edited it or reviewed it. In an advance that could dramatically reduce the amount of energy needed for crude oil fragmentation or fractionation, MIT engineers have developed a membrane that filters the components of crude oil by their molecular size. This is a whole new way of envisioning a separation process. Instead of boiling mixtures to purify them, why not separate components based on size and shape? The key innovation is that the filters have developed, it can develop separate very small molecules at an atomistic length scale, says Zachary P. Smith, an associate professor of chemical engineering at MIT and the senior author of the study. So, conventional heat-driven processes for fractionating crude oil make up about 1% of global energy use, and it has been estimated that using membranes for crude oil separation could replace the amount of energy needed by about 90%. For this to succeed, a separation membrane must allow hydrocarbons to pass through quickly and selectively filter compounds of different sizes. So they basically say, in this case, a hydrophilic monomer called MPD, which is dissolved in water, reacts with a hydrophobic monomer called TMC, which is dissolved in hexane, and the two monomers are joined together by a collection known as the amide or amide bond, forming a polyimide thin layer named MPD-TMC as the water hexane interface, or at the water hexane interface. Interesting. So there's a lot more over at this article. You should go and check it all out and then come back and talk with me about it. That would be great. If you want today's show notes, by the way, you can actually hit !TT for Technology Today, and ohmTown will spit out the articles. No particular order. That said, we've got one more article, and it's Earth's secret hydrogen jackpot, enough to power 170,000 years cleanly. Earth's secret hydrogen jackpot, enough clean power for 170,000 years. Natural hydrogen trapped in the Earth's crust could power humanity for millennia and without emissions. A new study maps out how to find it. Scientists from the University of Oxford, Durham University, and the University of Toronto have identified the key geological ingredients needed to find clean hydrogen beneath the Earth. I really think that hydrogen fuel cells is where it's at, but that doesn't seem to be happening. Not only fast swap hydrogen, right? You just pull a cylinder out, put a cylinder in, but coupled that with motors, electric motors in series, and you basically have my ideal car. Because all of this EV stuff is just a lost cause. It isn't defensible, and it's very High friction would be the word. Anyway, the article is over at SciTech Daily. University of Oxford put the article together. They say that the scientists from University of Oxford, Durham University, and the University of Toronto have identified the key geological ingredients needed to find clean hydrogen beneath Earth's surface. This natural hydrogen is produced by the Earth over millions of years and can accumulate underground in the right rock formations. The study shows that the conditions for trapping hydrogen exist in many parts of the world, making this a truly global opportunity. Hydrogen is already a $135 billion industry. It also is a cornerstone of future clean energy systems, with the market expected to grow to 1 trillion by 2050. This new research could help discover and tap into natural hydrogen reserves. And finally, the findings were published on May 13th in Nature's Review of Earth and Climate. So we'll keep an eye out for this. Yep. Yeah. Anyway, we are going to put in a new fuel cell, and that's going to snap us back to Technology Today over at ohmTown.com. And I'm going to get out of here. I am Mayor Watt. Oh, be sure to go over to ohmTown and become a citizen. Be sure to follow us, like, and subscribe on Twitch and on YouTube. And go over to the Patreon and subscribe there. Download all of the podcasts. There's a Discord. And yeah, that's it. I'm going to get out of here. See you soon.